All right, greetings everyone. The purpose of this video is to go over an example of finding the equation of a transformed toolkit function. And in particular, I think the most difficult part of determining the equation of a transform function is determining the stretch or compression factor. So I want to make sure I go over that. So start here. We've got given this equation and the graph there on the left. And they didn't tell us a name for it, so I'm just going to go ahead and call it g of x. So we need to find the equation of g of x. Now the first thing we want to do, since we know that it is a transformation of one of our toolkit functions, is to figure out which toolkit function it is a transformation of. And since we see that U shape there, that tells me it's a transformation of the quadratic toolkit function, which has the equation f of x equals x squared. Okay. And then when I am trying to find out the equation based on the base functions, so this function f of x equals x squared, that's kind of our base function, our starting point. One thing I want to do is identify how does this new function relate to, or what transformations have been made to change the function f of x into the function g of x. And to help myself with that, first thing I'm going to do is just kind of sketch what the original function f of x equals x squared would look like. So I know it would go through the origin, go through a point 1, 1, 2, 4, and then kind of be reflected on the left side of the graph, so here and here. And so then if I draw that, I can see that the blue graph there certainly differs from the graph that I've drawn in purple. So I want to figure out what it is. And so what I'm going to do, or what changes have been made. So what I'm going to do is I'm actually going to list out the transformations over here that I see. And since they're often easier to identify, I'm going to start by looking at shifts left and right and up and down. And so if I kind of focus on this lowest point of the graph there and compare it to the lowest point here, one thing I see is that the graph has been shifted to the left 1, 2, 3 times. So a shift of 3 units left. And then it also looks like it's been shifted down 1, 2, 3, 4, 5 units. So shift down 3 units. Or sorry, 5 units. Okay. And then it doesn't look like there's been a reflection of any sort, because if there had been, if the original function was reflected, we know it'd be opening downwards. And that does not seem to be the case here. But it does look like the blue graph compared to the purple one is certainly wider, which maybe gives us a sense that there's been some sort of a horizontal stretch. Also, it kind of looks, if we look kind of up and down, it looks like it's kind of been compressed a bit, so there might be some sort of a vertical compression. Um, but in both those cases, it's really difficult just from looking at the graph to determine what that horizontal stretch or vertical compression has been. So for right now, I'm just going to notate those. So there's been a horizontal stretch or a vertical compression, and those are the same thing. Okay, and now we have all the information we need to write the equation of the function g. So we'll start by doing that by just kind of going step by step through the different transformations we've identified. So first of all, since the function has been shifted 3 units left, we know that shifts left and right impact the inputs of the function, which means we notate that on the inside of the equation, which means that we have to do something in the place where the x is, because that's inside the function here. And since it's being shifted to the left 3, that might make us think we're going to do a minus 3. But you'll also perhaps remember from the given learning materials that when we have that shift on the inside, or when we shift left and right, that has to do with the house of lies. And so instead of being x minus 3, we're going to write x plus 3 inside the function. Again, it's inside because the x plus 3 is now in the place where the x was. So we've got that part. And then for the shift down 5 units, okay, well, when things are shifting up and down, that impacts the outputs of the function. So we notate that on the outside of the function. And in this case, there's no house of lies. So when it goes down 5, we just do a minus 5 there at the end. Okay. So far, our equation looks like g of x equals x plus 3 quantity squared minus 5. But then the next thing we have to do is to try to determine how much it's been horizontally stretched or vertically compressed. And again, it's really difficult to figure out kind of the factor by which it's been stretched or compressed just from looking at the graph. So what we're going to do to notate that is, first of all, we're going to assume it's a vertical stretch or compression, just because those are easier to determine than the horizontal ones. And because of that, we know that there has to be a number multiplied on the outside out front of the function to notate that vertical stretch or compression. So I'm going to use a variable a to stand for that missing stretch or compression factor. And then to help us solve for the value of a, what I'm going to do is I'm going to go over here and look at the graph and try to find a point for which I can easily read the coordinates. So for example, I don't want to use, say, this point right here, okay, that I'm trying to draw. There we go. Because it looks like that may be at like negative 0.2, negative 2.3 or something like that might be the coordinates there. It's just really difficult to tell, so we're not going to use that one. And we also cannot use this lowest point here, okay? This one right here. And part of the reason for that is, as you notice, we've already used that to determine how much it's shifted to the left and down. So we need to find a different point. And when I look at this, I see that this point right here seems to be, the graph seems to pretty solidly be going through that point, which appears to be at the point -7, -1. Okay, so I can read those coordinates fairly easily, so I'm going to go ahead and use those. And here's how I'm going to do that, is recall that when we have a coordinate point like that, it has an input and an output. In the case of our equation over here, we see that our input value or input variable is x, so we can think of that -7 there as being x. Our output is represented by g of x, so that -1 there represents g of x. And so what I'm going to do is replace those two values in the equation over there in their corresponding places. So what that'll look like is on the right hand side here, we'll have a times, and in the place of x, I'm going to put that input value from the point, which is -7. And then we have the plus 3 squared minus 5. And then on the other side of the equation, where there's the g of x, we're gonna replace that with the output value, which is -1. And so we get this equation that is -1 equals a times -7 plus 3 squared minus 5. And notice what we've done is we've created an equation where the only variable now is the variable a. And 9 times out of 10, when we have a situation like that, we can solve for the value of that variable. So let's go ahead and do that. So this will be now -1 equals, I'm going to leave the a. I start to simplify here, -7 plus 3, that's -4 squared minus 5. And then simplify a little bit more. So we have -1 equals the -4 quantity squared. That's 16 times a, which will make 16a minus 5. And then we just have a linear equation to solve. So we will add 5 to both sides. So we end up with 4 equals 16a. And then we can go ahead and divide by 16 on both sides. And when we do that, we end up with a equals 4 over 16. However, we can go ahead and simplify that fraction by dividing both the numerator and the denominator by 4, which will give us 1/4. So now we know the value of a is 1/4. We can go ahead and replace that in the equation up here. So what we see is that our equation of this transform toolkit function then will then be g of x equals 1/4 times x plus 3 squared minus 5. And that'll be our equation. And then of course we could go ahead and we could check this answer by plugging this, or not plugging, but entering this equation here into a graphing software such as Desmos and seeing does the graph we get match the one we were given. All right, that's it for now. Thank you for watching.